Hi, this is our second video on electrochemistry. So we're in chapter 20 in Brown and LeMay. All right, so far we've learned about galvanic cells, and we know that galvanic cells are spontaneous and that electrons are flowing spontaneously from the anode, where oxidation is occurring, to the cathode, where reduction is occurring. Now, the potential difference between these two electrodes is what is driving this to happen. And so this video is all about measuring that potential difference, and the units that we're going to use for potential difference is the volt. It's a capital V. A volt is a joule per coulomb. That will be useful later. All right, so the potential difference of the galvanic cell, as I said, is called the driving force. And I've just seen it called a bunch of different things. I've heard it called the electromotive force, or the EMF, or the cell potential, or the E of the cell, or the cell voltage. So that's what we're going to be calculating in this video. Some important points. You have a table of some standard reduction potentials, and these are in aqueous solutions at 25 degrees C. Now, you'll either have this chart in front of you, you can look in Appendix E in your textbook, or what you can have, sometimes in a problem, they'll just give you the reduction potentials for what you need. Now, if something is being oxidized, the reverse of the reaction is what would be happening, because everything is going to be written in the form of a reduction where the electrons are on the reactant side. But if something is being oxidized, and something will be oxidized in a redox reaction, then the reaction that's happening is the reverse of that reaction, and you will need to change the sign of the potential. So in other words, if it had a negative reduction potential, then it would be positive, or if it was positive, it would be negative. Then the other thing we need to remember, and this is something that we really haven't seen much before, the reduction potentials are an intensive property. That means it doesn't matter on how much. You do not ever multiply the potential by a number. You can change the sign if you flip the equation and make it an oxidation, but let's say that you needed to equalize your electrons and you multiplied an equation by 3, the number stays the same. Okay. All right, now let's do some practice problems. So calculate the standard EMF of a cell for the following reaction. And so I look at this and I see, oh, calcium is, in this case, calcium is being oxidized and cadmium is being reduced. And if I forget what oxidation and reduction are, I can look here. These are always reduction potentials. We're adding electrons. Here's the reduction potential for calcium 2+. It's a negative 2.87 volts. And here's the reduction potential for cadmium being reduced. And it's negative 0.4 volts. All right, but here we've got our calcium being oxidized, and so we want to flip that equation around, which means that is a positive 2.87 volts. And the cadmium, look how this equation down here matches what's happening up here, which means it's being reduced. And so we are going to keep that sign the same. It's negative 0.40 volts. And so when we add that together, we are going to have a cell voltage of, I have a cat trying to walk on the Wacom tablet, and I don't know if you've seen him walk. Here, come here, come here. This is the male cat, Zeus. Can you say hi, Zeus? Say hi. Yeah, you want to star in the video? Okay, so when we do this math, we're going to get a voltage of 2.47 volts. All right, let's try another one. So here we go. We have silver going to silver with an oxidation number of 0 because it's all by itself, and then we've got nickel going to nickel 2+. Notice that we had to add that 2 to balance the charge in front of silver, and then to balance the mass, you put a 2 over here. Well, silver is being reduced, it sure is, and here is its reduction potential. It's 0.80 volts. However, there are 2 of them up here. That's okay, don't change the number. Here we have nickel 2+. It is being reduced here. This is a reduction potential, but up here it's being oxidized, so we've got to change the the sign of that reduction potential, because in our equation up here, nickel's being oxidized. So that's going to be a positive 0.25. And so when we add those together, we are going to get 1.05 volts. Okay, easy as can be. Now, something has happened here. Both of these were for galvanic cells, and both of these voltages were positive. A galvanic cell is spontaneous, which means the cell voltage must be positive. Okay, now, this is something that College Board says that we really don't need to talk about, but you're going to see it in a chemistry Olympiad exam. You might hear professors talk about it. It's oxidizing and reducing agents. It is just kind of confusing. If something is reduced, it's gaining electrons, it is known as an oxidizing agent. And if something is being oxidized, it is a reducing agent. Now, if you have a very positive value, reduction potential for a half reaction, the more positive it is, the more greater the tendency for that reaction to occur. If you have a negative reduction potential, what that means, it's more difficult to reduce than hydrogen. Now, I didn't talk about the standard hydrogen electrode, the SHE, but all of these things have been compared to a hydrogen being reduced, and hydrogen's a gas, and you're probably thinking, how can we have that? You know, electrodes should be metal. But what they do is they just have a piece of platinum or some inert metal in there that provides a surface for the reaction. But anyway, if you've got a negative reduction potential, that means that it's more difficult to reduce than hydrogen. All right, so oxidizing agents are things that are easily reduced. They have high reduction potential. So if you look on your reduction potential table, fluorine F2 plus 2 electrons going to 2 F minus, 2 fluoride ions, it has a reduction potential of a positive 2.87 volts. That is the highest value on the table that I'm looking at. So it is the strongest oxidizing agent because it's easily reduced. All right. Lithium is the other case here. It's the most difficult to reduce. So when I look at its reduction potential, it's lithium plus an electron goes to lithium solid. It's negative 3.05, which means that it's a weak oxidizing agent. It doesn't like to be reduced at all. Common oxidizing agents, things that like to be reduced, are halogens, oxygen, hence the name. Things that are oxyanions, like permanganate ion, MnO4-1. The manganese in that has a positive 7 oxidation state. Dichromate, the chromium there has a positive 6 oxidation number. Nitrate, there the nitrogen has a positive 5. This is where these atoms have high oxidation numbers. So metals that have high positive oxidation numbers, being reduced is something they like to do, so they're common oxidizing agents. Reducing agents, so that's things that have a very negative reduction potential. And so lithium would be easily oxidized, and it is a strong reducing agent. So these metals, they like to lose electrons. They like to be oxidized, and so they're good reducing agents. Okay, now let's just talk about the spontaneity of redox reactions. If we have a voltaic or a galvanic cell, same name, these redox reactions will be spontaneous. You must come up with a positive cell voltage to indicate a spontaneous process. If they don't give you a balanced equation and you're supposed to figure out what's being oxidized and what's being reduced, make sure that you come up with a positive cell voltage. Okay, now, this is where our activity for series for metal comes from. So if you look at the metals on your reduction potential sheet, if there is a metal higher than another metal, that means that it is able to replace it. We learned that in standard chemistry. So if we look on our reduction chart, iron is high above silver, And so what that means is that iron can replace silver. And so iron, plain old Fe, going to Fe2 plus, will replace the silver, which would be in a solution with something. And we would need a 2 here and a 2 here and a 2 here. Okay, because the iron is oxidized, its potential would be, let's see, a positive 0.44. And the silver here is being reduced, and it is a positive 0.80. So this reaction would happen spontaneously because we're getting a positive potential. So again, this is where the activity series for metals comes from. And so for something to be spontaneous, you need to have a positive value for your cell potential. All right, so finally, let's connect this to free energy, because we've been talking about spontaneity, and we talked about that a lot when we talked about free energy. Okay, so blast from the past, please always remember that if something is spontaneous, delta G must be negative. And so now we know that for cells, the cell voltage has to be negative, and there is an equation that's connecting these two things. Okay, delta G is equal to negative NF cell voltage. This has got to be positive. This is a fancy F for Faraday's constant. It's given to you. It's 96,500 coulombs per mole of electrons. No, volts per mole of electrons. And N is the number of electrons that are transferred. And so, you know, when you're balancing that redox reaction, however many electrons you have to balance them out, that's what your value of N is. And as what you can see from this, now this is driving me crazy. Is it volts? Let me see. Faraday's constant. Excuse me. It's coulombs per mole of electrons. That's what I thought. There we go. I kept changing my mind. Coulombs per mole of electrons. There we go. All right. So you can see delta G's got to be negative. F is positive. E is positive. N is positive. That gives us a negative delta G. All right. And yeah, also remember that we said a volt is a joule per coulomb. And so now this is a coulomb, N is moles of electrons, so we wind up coming up with delta G having a value of joules, which is a great unit for free energy. Okay, we're going to practice this in class. Bye.